Is my screen is visible? Is my screen visible?
Yes, sir.
So let's start. So where were we in the yesterday's lecture? Yeah, yesterday we are done with both EM waves in vacuum and material. Basically, it's same as vacuum. Only mu and epsilon is replacing mu zero and epsilon. Now then we talked about, okay, we are done with what happens to a wave in a bulb. So what happens to a wave when it encounters a discontinuity? Okay. So when it encounters discontinuity, we call that discontinuity as a boundary. Okay. So to see what happens to electromagnetic wave at the boundary, we need to have a boundary laws in our hand, right? Then and then we can connect electric field and magnetic in one side of the boundary with the electric field and magnetic field on the other side of it. So before we go ahead and see what happens to an electromagnetic wave, we have to write down our laws for the boundary. So what are the boundary conditions for an electromagnetic wave or electric field and magnetic field? So let me write this. Let me write this as a boundary condition BC. Now we don't have a free charge, don't have a free current. Okay, nothing is there. So we got E perpendicular. So what will be here? E perpendicular above E perpendicular above, E perpendicular G, because there is no free charge. Now what about the E parallel? They are always equal to each other. This comes from the curl, because the curl don't have any charge or current included in the equation. It's simple that parallel components are continuous. The perpendicular components has a discontinuity, and that you can see from the, and it has a basically rho by epsilon c. Okay, so sigma things will come here. Okay, then what about B perpendicular? Always zero, because divergence of B is anyways zero. What about B parallel? Yeah, B parallel above upon mu. So let me write this as epsilon also. So let me write this one as epsilon 1 by epsilon 2. And this is mu 1. Multiplication, my mistake. Mu 2 is equal to 0. It should be multiplication. So let me write the equation again. So epsilon 1 E perpendicular above minus epsilon 2 E perpendicular. The reason I am writing epsilon 1 and epsilon 2, because both the sides of the boundary epsilon will be different, and same thing for mu also. Okay, so our boundary conditions are in line. Okay, we got this boundary condition. With this boundary condition, we'll connect the electric magnetic field from one side to another side. So let's write the electric field and magnetic field for a wave. Wave is nothing but electric field and magnetic. So let's write it here. So let's divide now. We got two areas. So this is a boundary. We got a material 1. We got a material 2. Now let's say that EM wave is, this is, I said, this is a Z direction. This is a Z direction. Okay. And say boundary for a simplicity. so that our equation becomes 0. This point is basically z. So this boundary is basically z is equal to 0. That's the point. Now let's say that upward is y direction. So upward is x direction. Yeah. So this should be x up. If I put x up, no, that's why I'm putting x up. So y will be coming outside. Okay, y is coming outside, x is up, and z is the. Now let's consider that our wave has the electric field in the x direction. So this is the electric field. Let me call this as EI. When wave is traveling in z direction, that means what will be the direction of B? It is E cross B, y direction, outward. So this is BI. Okay, I'm calling it as an incident because this is the way which is going to hit the surface. Okay. Now, if this is the wave, okay, which is traveling in this direction, so let me call it SI. Right now, what will happen to the wave here when it encounters a boundary? What should happen to a wave? Either it should get reflected back, or it should continue its path in the same direction. Right now, we will consider both the possibilities. We don't know which is going to happen. We'll consider both the possibilities. So let's consider that wave is also going in the opposite direction. So let me call this as SR, a reflected pointing vector for that wave. And let's say that our electric field for that wave is also ER. So what will be the direction of magnetic field? E cross B, so it will be inward. So magnetic field will be B. And here again we will consider, let's say, the magnetic field which is in the second, which continued in the same direction, as E transmitted. Okay, and this is B transmitted, and your S as the direction of this. Now the question is that why we have considered EI in the upper. This is okay because we have continued in the same direction. ET and EI having the same direction is okay. But what about ER, which is going in the opposite direction? I have considered that ER in the same direction as EI. Okay, the question is why? So as a starting point, we don't know anything about ST, SR, SI. So it hardly matters to say that conservation, because something might be higher and the negative part also comes, right? One second. So in this particular case, let's start with this part. Let's see what happens. Okay. So I'm assuming it to be in the same direction. Now, as we don't have much information, let's assume that in the same direction. Now, the direction of E is called as direction of the polarization. Okay, direction of E is called as direction of polarization. So wave which is coming, incident wave, has a polarization which is upward in the x direction. Wave which is getting transmitted has the same polarization which is also along the x direction, and wave which is getting reflected also has a polarization in the x direction. Okay. Now suppose, what about BI? Now BI and BR are out of phase. They have the same direction, Y, but they are out of phase. But BT is in phase with BI. Now when we go from 1 to 2, something will change because there is a different material. So we know that their speeds will be different. So this will be V1, this will be V2. The speed will change because of what? What about we have two more parameters, frequency and wavelength, right? Now, which one is supposed to change when you go from one material to another material? Wavelength. Why not frequency? Have you asked this question? Why not the frequency is changing when you go from one material to another? The wavelength is changing, but why not the frequency? Okay, that answer is not in front of you, right? I have not opened that box in front. Right. So a frequency of electromagnetic wave is not because of the material itself, but because of the source of this EM wave. Okay. Now wave which is getting reflected back and transmitted and the incidence, all these waves have the same common source, right? Which is somewhere else. We are not bothered about that source at all. We have got detached from the source, and then we are just looking at this, looking at the wave, not the source. But source is same for all these three waves, three possible waves, two possible waves. One is incident wave is already there. Transmitted and reflected wave is something which is possible. They may, if they are not possible, we'll get answer as 0 for them. Is it clear? If they are possible, we'll get some amplitude. Okay. So basically, your frequency is a function of the source, not the medium. So frequency remains the same. What changes is the wavelength. As soon as the wavelength changes, what else will change? The wave vector, wave number, right? So you will have different. So your change in the speed is basically a reflection of change in the wavelength. So you got K1 here, you got K2 here, right? So let's write equations for this. So let's write first for the incident. So you got EI, okay, is EI0 e raised to I K1Z minus omega t, and you will have BI is, now we can relate EI and BI, so we don't have to write BI0. We can just write EI0 divided by V, right, into e raised to I. Now it is in the same medium traveling in the same direction, so we got K1 Z minus omega t. So it is V1, sorry, yeah, this is V1, K1. Then you got a reflected one, so which is ER, okay. This is X cap, this is my screen is visible to you guys? Hello, Srishti, Joel.
Sir, it is visible.
Yeah. Okay, so we got ER also. So ER will be ER0 e raised to I k1z minus omega t x cap. Here it should be y cap also. And we got b. Minus sign we should. So because it is in the opposite direction. So k1 minus k1 shows the negative direction. And it will be ER0 divided by again V1 but with a minus sign because minus y cap e raised to I minus of k1z minus omega t y cap. So these are your two waves. So this is incident and this is reflected. Okay. Then we got a transmitted. Transmitted wave is ET is ET0 e raised to I. Now this will be k2 z minus omega will be same omega. This will be also in x cap and in dt is ET0 upon V2 e raised to I k2z minus omega t y cap. Okay, so when they are in bulk, once the reflection and transmission is done, they are just like other waves traveling in the bulk. So that discussion we have already done. So there is no point of discussing before the electromagnetic wave encounters the boundary and after the encounter. So both the things are immaterial because we already discussed that how the wave travels in the medium. But the question is that when it sees the boundary, what happens? So when this electric field and magnetic field sees the boundary, they have to follow the boundary conditions, which we already have. So we can apply the boundary conditions for the left hand side, medium 1 is equal to right hand side, medium 2, right? So what are the first boundary conditions? Now here it will be epsilon 1 EA1 perpendicular minus epsilon 2 E perpendicular B is equal to 0, right? Similarly, the other things. Now, if you see here, what kind of component we have? Do we have both components of E and B, or we just have a parallel component, or we just have a perpendicular? So we just have a parallel component because our boundary is XY plane, right? Or all the fields are in either in X or Y. So we just got a parallel component. So this equation 1 and equation 2 are 0 is equal to 0. Now what we have is equation 3 and equation 4, right? So here we says that equation 3 says that parallel component on one side should be equal to parallel component on the other side. And with z is equal to 0. So when z is equal to 0, what happens? K1z minus K1z minus K2z, all those components will be 0. Minus omega t is same everywhere. So when we do a equality of the boundary condition, one side is equal to other side, those also get cancelled. So what remains is the amplitude, complex amplitude. That is what remains. So we'll write everything in terms of amplitude. So let me write in terms of amplitude. So from the boundary condition, can anyone tell me what will be the first boundary condition? E parallel on one side is equal to E parallel on the other side. And everything is parallel. So for electric field it is EI0 it is, right? This is the first boundary condition. What about second? So EI0 V1. So you got 1 by mu1, which is the left hand side mu1 will remain same for incident and reflected. So I'm writing here I 0 by V1 minus, so this will be plus, but we have a minus ER0, right, upon V1 again is equal to 1 by mu 2 ET0 upon V2. Okay, and as we were discussing yesterday, because susceptibility of magnetic materials is very much less than 1. Okay, permeability, which is a mu, is almost equal to mu z. It's not very different. Epsilon changes dramatically when you go from one metal to another, but mu remains almost same. Okay, so mu1 is equal to mu. Okay. So basically, what we get this equation as EI0 minus ER0 is equal to V1 upon V2. So let me write these two equations. Now we got two equations and we got two variables. What are those two variables? Can anyone tell me what are the variables I am talking about? I am making a statement that we got two variables and two equations. What are the equations? What are the variables I am talking about? Yeah, because incident is in our hand. We can decide how much electromagnetic wave we should shine on the boundary. So EI0 is something is always given, right? What is not there is reflected and transmitted. That is a totally condition of the boundary. V1 upon V2. Okay, we can solve this equation. Can anyone just solve this equation and tell me? So basically what we want is EI0, sorry, my mistake, ER0, and that should be as a function of EI0, because EI0 is something which is always in our hand. Yeah. So suppose we subtract these two equations. Okay. V2 minus on V1 plus V2, right? And what about the second one? 2V2 upon V1 plus V2. Now looking at these equations, we got now relationship between something which is given as an input from our system and output we are getting, both are we have. Now let's look at the properties. Now what are the properties of this one? If you look at E transmitted, okay, it is always positive with respect to EI0. So that means this term in the bracket for the second equation. So let's look at the second equation first. Term in the bracket of the second equation is always positive. So this is always positive. What does it mean? If EI0 is positive number, ET0 will be also positive number, right? So they are in phase, right? Because e raised to I delta I is equal to e raised to I delta, sorry, delta T, my mistake. Let me write this way also, that is all. They are equal to each other, right? So your transmitted wave is always in phase with the incident wave, no change. What about the reflected wave? So it depends on V2 and V1. If V2 is greater than V1, they will be in phase. Okay. So if V1, you got e raised to I delta R is equal to e raised to I delta I. Okay. If V2 is less than V1, then e raised to I delta r is equal to minus of e raised to I delta r, right? And what minus sign shows? So yeah, e raised to I theta is equal to cos theta plus I sine theta. So you have to see when this term becomes minus 1. That is when sine theta is, sorry, theta is pi. Because cos theta will be minus 1, sine theta will be 0. So e raised to I pi will be minus 1. So that means it's like instead of minus, you can add e raised to I pi. So basically delta r, this implies that delta r is delta I plus pi. That means they are out of phase if V2 is less than V1. So even though we are considered in our first assumption that both are in the same direction, that assumption is remains as it is when we have a V2 greater than V1. But as soon as V2 is less than V1, we get minus sign introduced and reflected wave is out of phase. Okay, and that type of thing you can see easily even in the material waves. Like suppose you take a string, okay, attached to a lighter string and oscillate. Okay, so the end point of the first string and starting point of the other second string, the reflected wave will be always in phase. But suppose you take a string and tie it to the say wall, and now you oscillate now you create a wave on the string. What will happen? The wave will get reflected back. Okay, something will be transmitted as a disturbance inside the wall, but something which is getting reflected back, you will see that that is out of phase compared to the incident. Same thing happens for the EM waves, not very different. Is it clear? Okay, but this is what, these are complex amplitudes, right? Now we can write in terms of their real amplitude. We have to set mod here, saying that the phase angle is taken out. Okay, so we got amplitudes. But amplitudes are not something which we measure. Finally, we have to connect everything to a measured point. Because then and then we can check the theory. So what we measure? The intensity. And yesterday only we have seen how we write intensity. One half C epsilon naught or epsilon, only epsilon 1, epsilon 2 will come into E square, amplitude of E square. Okay, so now you can find out intensity I of reflected wave. Okay, that you can find out in terms of intensity of the incident wave. Okay, similarly you can find out intensity of the transmitted wave in terms of intensity of the incident wave, right? And we know that the energy is conserved, right? So total intensity should be intensity of the incident wave. So equal to IR plus IT. That means whatever inside this bracket, they should become 1. Simply, they should become 1. So say let me call this as A, or let me call this as capital R connected to the reflectance. This is capital T. So R plus T should be equal to, is it clear? Okay, this is called as reflectance and transmittance ratio. So basically what we are doing is that instead of looking at the absolute values of the intensity, let it make a generalized state. So what is the percentage of energy which is getting reflected back? What is the percent of energy which is transmitted? And percentage should become 100% or fraction should become 1. Okay. So if you do any experiment, what you should get is something this. Is it clear this part? You can do this type of experiment. What you can do is that you take a, say, glass slab, shine a light from one side where you can measure the intensity. Now there will be two reflections. First one, air and glass. Next one, glass and air. Okay. And outside you can measure what is the intensity that is transmitted in both the cases. Now there will be two reflections together. So you have to consider that way. Okay. And you get a reflected intensity. That also you can measure because that comes back towards the laser or source of light. You can put a sensor there also, and looking at them you can find out what is V1 V2 because it will give you IR and IT. Once you get IR and IT, they are connected to R and T. So basically you get R and T. You get R and T. R and T will inbuilt it will have V1 and V2, right? So you can get a ratio of V1 and V2. You won't get absolute values. For that you need to know at least one value. Okay, you will get ratio of V1 and V2. A simple experiment which can be done at the FIBSC level also, but it gives you a lot of information looking at this equation. Is it clear this part? Okay. How much time we have? 10 minutes. Now I have one more question which no one has. First question is answered, that is the reflective wave is in phase, even though it is shown here it is in phase, it is not. Okay. Now the second question, I am showing, we are assuming that EI, ET and ER all are in phase. So all are in the same direction. They may be out of phase, but they are in the same direction, X direction. If EI is in the X direction, ER and ET both are also in X direction. But this is our assumption. Is it true? May or may not. We are not checked. We assume that. I just made that statement while writing here. ET is also in X direction and ER is also in the X direction. And just started with that. No one asked this question. Might be you are also assuming that is the way. But question is that if that is the way, we have to prove it by someone. So, yeah, it's by experiment. That is verification. See, you can give a theoretical proof and you can verify by as the same experiment. You can find out what is the, you can take a laser, see the polarization, make it vertically polarized, okay, and see what is the transmitted light, what polarity of that transmitted light is. Is it the same or is it different? Look at the reflected light. Is it the same or different? Both the things we can see. But how will prove theoretically? So consider a general case. So you got, say, instead of EI is in the X direction, but ET and ER not in the X direction. So basically they have a, ER has this type of thing. It has an angle theta R with X direction. There is a theta R with X direction. So you get basically ER as cos of theta R X cap plus sin theta R Y cap. That is okay. Similarly, you will get cos of theta T, okay, X cap plus sin of theta T Y cap. Now what you will do? Now you have one side ER, one side ET. The boundary conditions still follow, right? They are independent of what kind of things you have. So you can just compare X component with the X component and Y component with the Y component. And from there you can show that this theta R and theta T are nothing but 0. That means this is an angle with respect to X, theta R and theta T. So they are 0 means they are in the same direction of transmitted and reflected. Is it clear this part? Okay, I have two questions. Like, suppose we got a diamond, just a simple question, a substitution type of question. We got a diamond and air. There is a diamond at air. Now question is that what is, say diamond has a refractive index of 2.5. Okay. Then what is R in this case and what is T? So if you have a light, if you have an electromagnetic wave, okay, coming from the air side, how much, what is the fraction of light which is getting, how fraction of electromagnetic wave which is getting transmitted and fraction of electromagnetic wave which is getting reflected. Now you got a refractive index is 2.5. So what is the refractive index? It is connected to the velocity. So velocity is inversely proportional to the refractive index, right? So we had V2 by V1, which can be written as N1 by N2, right? So V2 and V1 can be simply replaced by N1 and N2. So whole equation can be written that way. Okay, once you got that, you can just find out what is the T and R. Now I have not written the final formula here. I just wrote it like this. You should feel. Don't go to the reference book and check. We are done up to this part. You can just take this as a starting point and find out IR and IT and R and T from there. Okay, then you can find out for air and. Okay, then there is a next question. Let's say we have a material called as X. So there is an air on one side and there is a material X. Now find refractive index N for this material. Now what is the condition on this? What is the properties of this material? Is that R is equal to T. This material is such type that if you shine an electromagnetic wave, okay, what happens? 0.5% is transmitted and 0.5% is reflected. It's other way around. You don't know what is N2 and N1. Okay. So sorry, N you don't know. This N is basically, you can take it as 1. Right? So your N1 is 1 and you have to find out N2, where R is equal to T is a condition which is given to you. Is it clear? Next time what we'll do, we'll take a more generalized case. Next time what we'll do, next time, previously we had an electromagnetic wave which has a component only parallel to the surface. Now we'll see, look at the component which are not parallel to the surface, or transmission which is not parallel. So we can take a transmission like this. So you got an electromagnetic wave which is coming at particular angle. What happens to them? That we'll see next time. Okay, so I'll stop here.